Okay. Yeah, I'll just take it away. So, hi everyone. My name is Oscar Skean, and I'll be presenting my work layer by layer, uncovering hidden representations in language models. This work was accepted to ICML this year, 2025. Yeah, and so I'll just dive right in. So, a little bit about me before we jump into the work itself. So, I'm a fifth year PhD student at the University of Kentucky, and that's in Lexington, Kentucky, in the United States. My background is generally like kind of the intersection of information theory and representation learning. It's been pretty domain agnostic. So I've worked with images that are object-centric, medical images, text data, tabular data, and my work kind of centers around this notion of representation entropy, which we'll get into later. It's a big part of this work. And I've done a couple applied machine learning internships at Stripe where I've worked on like tabular data, like large language models for tabular data and so on. So yeah, pretty domain agnostic. I've dabbled in a lot of fields, but this work is about text, of course, language models. So my co-authors for this work was purely like kind of distributed. Like we collaborated on Discord, so everyone was kind of spread out at different universities. Yeah, and it was yeah, just a great group of collaborators. So just an overview of the work. So I like to frame this work as challenging a couple common assumptions in modern ML folklore and practice. So um, like there's like these myths or like just things people always do. Like people take a model from Hugging Face and use like the final layers of their output, uh, final layers of the model as their output for whatever task they're doing, or they train a model and then just use the last layer to generate things. And this is like something people don't question too much. It's just the way things are done. But uh, that's not quite true. Like we'll show in this paper that final layers don't always give the best embeddings, and you can oftentimes find um, much better embeddings in the intermediate layers of the model. And kind of a second myth is that middle layers are useless or hard to use for downstream tasks. And actually, it's quite easy to use them for embedding tasks and also generative tasks as well. So we'll talk a little bit about both of those. And so, in the reality, just being, intermediate layers often outperform final layers, and it's not too hard to try it yourself. Um, so we show that intermediate layers outperform final layers on many downstream tasks. We do like pretty rigorous empirical testing across different model architectures, scales, different tasks and modalities. So we look at language and a little bit of vision as well in this paper, just to show how generalizable our findings are across domains. And we also introduce a theoretical toolkit of evaluation metrics to explain internal model phenomenon and explore why these intermediate layers are so strong. And just to kind of fit this work into the broader research landscape, I think in any ML field, so like we see this a lot in vision and language and also audio too. Like people are all the time observing emergent phenomenon, like things that the models are capable of, but they're not necessarily trained for. These kind of surprising things about large models that are kind of emergent at scale. And these emergent phenomena unlock new capabilities. So you can use your model for new tasks that you didn't previously think of. You can get performance improvements. You can understand how the model was trained a little bit better. Um, and so this is like a really nice thing to be able to take this artifact and find a new way to use it. So our work does this for language models, and we have this information theoretic explanation for why this intermediate layer emergent phenomenon might be happening. Okay, so have we'll start with the empirical experiments on our embedding benchmark, and then later on we'll talk about the theoretical evaluation metrics, and just lastly close with some implications of the findings. So starting with the empirical results. So the very first thing we looked at in the paper is we evaluated just how the intermediate layers perform on downstream tasks. So we started with the massive text embedding benchmark. So this is a state-of-the-art benchmark that's like really, really well implemented from Hugging Face. In the benchmark, there's over hundreds of tasks and different languages and different task types. So you have like semantic understanding, you have like translation tasks and so on. So we chose 32 diverse tasks spanning 5 different task domains, and we'll talk about little on the next slide, like the task domains. And our goal was to probe every single model layer in a variety of models and to see how they do. And we wanted to see which layers create the best embeddings to train a classifier on. So here's the list of tasks that we did. Roughly, these are categorized into 5 task domains. So pair classification, like do these sentences follow each other or not? Kind of like how the BERT model was trained initially, like that was part of the pre-training task. You also have classification, clustering, re-ranking, and sentence-to-sentence tasks. So there's more tasks in the data set or in the benchmark itself, but we just narrowed down to these 32. And here's just one little example from the Amazon Reviews classification data set. So our prompt that we would give the model is classify the given Amazon review into its appropriate rating category. And here's like an example of a review. And the model is not actually generating this, but we're like passing the embeddings to a classifier. And I want to note that this little prompt header in bold here, which is like describing the task the model is doing, this is implemented in the benchmark. So that's not something that we did for the paper. This is like very standardized in the benchmark, and any paper that uses these has the exact same prompt. So it's like pretty well implemented, as I said. Um, yeah, here's what the protocol actually looks like. So we have our tokens. We pass them through the model, and we stop at layer K. And then so we have our representations for the tokens at this intermediate layer, and we use these representations for this classifier probe. And for this probe, again, this is implemented in the benchmark, so that's not something we implemented ourselves or designed the protocol. Um, yeah, so we'll just jump to the results. And so we have here 3 different models, Pythia, Mamba, and BERT. So these are kind of representatives for 3 different model families. And across the board, so on the x-axis, we have layer depth percentage, which 100% is like the end of the model, and 0% is the first layer. And I'm showing layer depth instead of layers because these models have different numbers of layers. So just to make them easily comparable, we're looking at depth. But across the board, uh, all 3 of these model families have very, very strong intermediate layer performance. And so Pythia is a representative of next token prediction transformers. BERT is a masked language modeling transformer. And Mamba is a next token prediction state space model. So 3 different families all having the same pattern where there's um, some intermediate layer where there's high performance. And in some cases, it's quite drastic. Like Mamba, it's pretty substantial. Like it's about 25 percentage points from the last layer to the best intermediate layer. And I should also say the way we're calculating this average main score on the y-axis is just for all of our 32 tasks, the benchmark gives a main score, and we're just kind of averaging this across the board. Um, so it's comparable and it's pretty striking, this trend. And also, we didn't talk much about this in the paper, but this was asked about in the rebuttal section. So, and I think it's worth mentioning, it's very interesting. So these findings are not just for embedding tasks, but also for generative tasks. So it gets a little bit tricky, like how do you get tokens from intermediate layers? There's 2 techniques that I know of that are out there. So there's logit lens, which is it was actually, I think, introduced in like a blog article by Nost algebraist. And this was um, improved upon by Luther AI and a work called tuned lens. And both of these techniques give ways to get logits from intermediate layers. And essentially, it just boils down to um, uh, for tuned lens, for instance, you just train a unembedding layer. So like for every model layer, you train some token classifier, like the unembedding layer. So you can get logits from any layer pretty easily. And so we took some off-the-shelf logit tuned lens uh, unembedding layers for a Llama 3 8 billion. So these are already trained by Luther AI, so we just pulled them and looked at how Llama 3 does on the MMLU benchmark data set, which is also very standard and a good benchmark. And here we see it looks a little bit different than the previous task, where there's kind of this parabolic shape. But here we have the same phenomenon of like there's this big jump around layer 16, and it's kind of flat from layer 16 until the end of the model. Um, and there's, I think, layer 26 is about 1 percentage point better than the last layer, which is layer 32. And people that are interested in model efficiency might even just chop off the last half of the model and just use that like peak right there at layer 16. So you can essentially chop off half the model and get pretty decent performance as compared to the last layer. Yeah, so now we'll jump into this theoretical toolkit of evaluation metrics and kind of probe why this might be happening in these models. So very similarly to our earlier experimental pipeline. So again, we're taking our prompt, we're passing it through and getting representations at layer K, but and this time, instead of training a classifier probe, we are using these evaluation metrics. So there are three types of evaluation metrics that we discuss in the paper. And in reality, there's like many, many more out there that you can try and examine your model with, but we just focused on these three families of evaluation metrics. So the first family is information theoretic, which measures how much data is preserved in the representations. So we call this, so there's like a notion of prompt entropy that we discuss in the paper, and we'll get into that more in a couple slides. And there's a couple other information theoretic metrics we look at. There's also augmentation and variance metrics, which is measuring how stable the representations are. So for this family of metrics, this one's pretty interesting and kind of this is inspired by vision literature, where you take some image, or in this case, text, and then you make a copy of it and add some perturbation to it. So for text, you might add some typos, you might add some random words or some, spacing, just kind of perturbing it so it keeps the overall semantic meaning, but you have these like little noisy features that are present in the prompt. And the goal for the augmentation and variance metrics is just to see how invariant are the models to these noisy features. Because ideally, like in a perfect world, a good model will be able to look past the typos and understand what your prompt is actually trying to say. And the last metric we look at is geometric, or really it's just curvature that we look at, which is measuring the shape of the data. How is the data spread out over time, like over the sequence? How curved are the representations? So within these three families, there's six metrics we look at. Kind of my favorite, to be honest, is prompt entropy, because that's my background working with this metric. And so it's an information theoretic metric, and it's a central link also. We have a couple of theorems and lemmas that link prompt entropy to the other families of metrics. So for the purposes of this presentation, I'll just be focusing on prompt entropy, but if you're interested in these other ones, we go into depth on them in the paper. So prompt entropy, I'll just briefly describe how we calculated it and also what are the interpretations of it. So first, to actually calculate it. So we take a prompt with n tokens and do a forward pass of the model. So the outputs of each model layer are an n by d matrix. So for each token, you have a d-dimensional embedding or representation. So the way we actually calculate prompt entropy is we take the covariance matrix of those representations and we calculate what's called the effective rank of that covariance matrix. And all this is we take the eigenvalues of this covariance matrix and calculate the Shannon entropy of it. So we have here just the Shannon entropy equation. So we're taking the Shannon entropy of the covariance matrix eigenvalues, which are denoted here in as lambda I. So lambda I is the ith largest eigenvalue. And there's a couple clear interpretations of this metric. So for high entropy, so a high entropy distribution means that in this case, all of the eigenvalues are roughly equal. And so that means the data is spread out equally in all directions. If you think about the principal components, like you don't have any eigen directions that are dominating the space. So if the eigenvalues are roughly equal, the data is spread out, this is a high entropy, which means that the covariance matrix is high rank, and the tokens are very spread out and contain a lot of non-compressed information. Like each token is pretty unique, and there's not a lot of redundancy across the tokens. At the other end of the spectrum, if there's a couple very large dominating eigenvalues and you have a long tail eigenvalue distribution with a lot of small ones, we have a low entropy. So this means the matrix is low rank and there's a lot of redundancy. The tokens are very compressed. Um, and so what we do is we calculate prompt entropy at every layer in the model. Um, and I also just wanted to quickly raise a couple prior work. So as I mentioned, my background is in prompt entropy. So if these kinds of metrics are interesting to you, so that like for a gentler introduction into it, I have a paper called DIME, which is like looking at prompt entropy and mutual information. I really like the exposition of that paper, and we actually use DIME in this work, the layer by layer work, as an augmentation invariance metric. So if you're interested in that in general, I would check that out. And you can also use this prompt entropy or representation entropy as a regularizer to improve convergence rates of your model. So I have some prior work in the self-supervised learning vision domain where I essentially just add a regularizer, so I'm maximizing the entropy of the representations, and this actually improves the convergence rate of the model, and you need less training steps to train. Yeah, so prompt entropy is very useful. But jumping back to our work here, so layer by layer, we're looking at it across all the layers. And so again, we're looking at the same three model families here. So Pythia, Mamba, and BERT. And we see here like three very different trends. And here's where the paper really starts to get interesting, I think. Because for all of the metrics we look at, each model family has its own kind of fingerprint or unique way they behave internally. So I'll just linger on this slide a bit and just explain what we're looking at. So again, we're looking at normalized prompt entropy on the y-axis and x-axis is layer depth. And so we'll start with BERT because that's probably the simplest to understand. So BERT prompt entropy remains fairly high, so it's like it's around 0.9. One is the maximum, it's normalized. So it remains fairly high across the layers. There's really no compression going on. And we see this across many masked language modeling models as well. So it's like BERT, we're just showing BERT here, but really these are representative of the families of masked language modeling, and it's pretty stable within the whole family. Pythia, and again, next token prediction models in general, llamas, OPTs, quins all have this behavior. Pythia is very interesting because it's flat at the beginning. So the first 5 or 6 layers, there's no compression going on. And then all of a sudden there's a big dip. It compresses a lot in the intermediate layers. And it stays compressed. And then at the end, it decompresses. So there's two interpretations I like to say here. So the first one is you can think of this almost like an autoencoder. So even though next token prediction models, Pythias, are decoder-only models, we see here kind of a compression and decompression uh, framework. The model is compressing and uncompressing, just like an autoencoder would do. So this decoder-only model secretly inside has this encoder-decoder. So that's the first interpretation. And the second interpretation, there's some prior work from Max Tegmark's lab, and we cite this work in the paper, which looks at different phases of the model. And so they claim that the first few layers of the model are what's called a detokenization, which is going from token space to an abstract idea space. And they claim that the model is operating in this idea space, like that's where the most of the, there's concepts in the space, there's abstract semantic concepts, and that's where the model is doing most of its operating, its processing. And then at the end, there's a retokenization phase where the model, is trained to output tokens. So the model kind of converts from this abstract idea space back to token space. And so that's some prior work, and I think you can kind of interpret this that way. So the first few layers that are flat are doing this detokenization, and then the compressed space is the more abstract region of the model, and then it retokenizes at the very end because the model needs to output tokens for its pre-trained task. And then the last one on this slide is Mamba. Mamba is pretty interesting as well because it's doesn't really compress until the very end. And there's a couple hypotheses for this. I guess the main hypothesis is that the linear attention of state space models in Mamba is not complex enough to do the compression, to do the early compression that is present in the more complex quadratic attention that we see in the Pythia next token prediction style of models, the transform models. So yeah, all three families are pretty interesting and diverse. Yeah, and actually this for a little bit of background, like this is actually the very first plot we made in the paper, and everything else kind of was built around this, trying to understand why this was happening. Um, but the most interesting takeaway is just that autoregressive models exhibit a strong intermediate bottleneck, and that the model architecture and pretext tasks really influence the internal behavior. So Pythia, we focused on Pythia in the paper because they are very great and they release all of their training checkpoints. So you can do a lot of training dynamic understanding by like just stepping through all of the checkpoints and just seeing how things change over training. And so we do this for all of the metrics in the paper, but I'm showing here prompt entropy. And we see this bottleneck emerging during training. So there's 143,000 training steps in Pythia. So I'm showing here just some equally spaced training steps throughout the model training. And pretty early on, the model starts to learn to compress like this. So it starts pretty flat, so it's pretty pale and hard to see. It almost starts as the initialized model um, essentially does not compress at all. It looks like the BERT on the previous slide. And then as the training happens, like you see this dip start to form and it becomes more and more profound. And then at around 100,000 steps, it kind of locks in at the bottom there and doesn't really move much. And the other thing that's interesting here is that the first five layers, the first six layers are pretty static and don't change at all during training. Um, and which that's just interesting. So you would expect that, as you're training a model, all of the weights are moving, but we don't really see a change in behavior in the first five or six layers. And I'll also say, so it's hard to see if this generalizes to other non-Pythia models because, as I said, Pythia releases the training checkpoints, and that's a rarity these days, with all of the foundation models being trained internally. So it's hard to know how this one generalizes, but I'm hopeful that it does. Uh, and so something else we see, we also look at Pythia, is that bigger models indicate a stronger compression. So I'm showing here Pythia models ranging from 14 million parameters all the way up to 1 billion. And really, you could go farther. I believe there's an 8 billion or 7 billion parameter Pythia not shown here. Um, but we see that well, first of all, even the smallest model has a little bit of a dip in the middle. So the 14 million parameter model, the middle layer at 50% depth is the most compressed. And as we scale up the model to more parameters, we just see it dip more and more and more. And we see the drop point become earlier and earlier in the model percentage-wise, but really it's always around 4 or 5 layers. but it just because the models are scaling up and there's more layers, that shifts become more relatively early. Yeah, eventually, yeah, the largest model is the most compressed, and yeah, I would expect as you scale, as you keep scaling up, the compression keeps becoming stronger. So another interesting takeaway is that in autoregressive models, a low entropy correlates to a high downstream performance. And really, this is just looking at the fact that the intermediate layers on the left have a low entropy, and on the right, they have a high performance on downstream tasks. And this is for the massive text embedding benchmark. And so you can make use of this to find a good layer in an unsupervised way. So, this is like a technique. There's been a few papers in the vision domain about this, and we kind of adapted this to the language domain. So, if you want to find a good layer in an unsupervised way, or really in general, like the approach is to train a probe and like just train a supervised probe and find the probe with the best performance. But that's a lot of work, and you don't always have labeled data. So instead, what you can do is use these unsupervised metrics to find a good layer. So you can find a minimum entropy, or you can use the other metrics that we present in the paper. And in this fashion, you can find a layer that can give a 5 or 10% performance improvement on your particular task with no additional training. And all you need to do is a few forward passes on your data and just monitor these metrics. So we have this table in the paper which does this. So for Pythia and LLM Tvec, which is a fine-tuned llama model, we're looking at a few different ways to get intermediate layers. So the baseline here is what's denoted as naive. We're just taking the last layer, and so this is our baseline, and you know, finding any intermediate layer that can outperform this is a big improvement. So the the straightforward solution is to train a supervised linear probe. So we call this best, like the best layer. That's the second to left column. This is kind of an upper bound for the performance improvements you can expect. But you can also use our unsupervised metrics. So we have here DIME, which is the augmentation invariance metric, info and CE, which is also augmentation invariance and dataset entropy. Uh, so using three of these metrics, we're monitoring them and like choosing the layer that has the minimum of these metrics. And you can get like a 3% improvement on average for Pythia by minimizing DIME. And for particular tasks, it can be up to 10% improvement. But really, it varies quite a bit per task because some tasks are harder, some tasks are easier. But on average, it's a 3% improvement using DIME. And even for LLM to VEC, it's a more marginal improvement with info and CE, but it's still, non-trivial. Like it's a 0.4% improvement. And then this is purely, again, unsupervised, just looking at these metrics across the layers. So finally, like we look at how well does this work extend beyond language models. So in the vision domain, I always think the vision domain is very interesting because there's a rich selection of models trained on many pretext tasks. And really, there's probably hundreds of papers proposing new pretext tasks and different ways to train vision models and do augmentations in a self-supervised way. So it's just very rich, and you can like really look at how pretext tasks influence the model training. So we looked at SimCLR, JEPA, MAE, Dino, and a couple more, and we checked this modality to see if our findings hold across domains, and also how the pretext tasks influence the internal representations. So our main finding is that autoregressive vision models show the same pattern. So AIMV1, which is it's AIM stands for autoregressive vision model, autoregressive image model. This is a paper out of Apple, and where they essentially do next patch prediction instead of which is the proxy for next token prediction. Um, we see a very similar trend to what we were looking at earlier with the Pythia next token prediction models. So for prompt entropy, we see AMV1 is the blue line here. So we see it's flat, and then all of a sudden there's a big dip, and then it kind of increases again at the end. And on the right graph, so we're doing validation accuracy on ImageNet. There's an intermediate peak around layer 15 or so, and then it goes up to layer 15, and then it starts decreasing towards the end. Um, there's been some prior works in vision that have like there's one that comes to mind called guillotine regularization, where they find that chopping off the last few layers of the model can oftentimes lead to improved performance. And we kind of see that here. We see a justification for that here, just in terms of we're seeing this intermediate peak. Now, it's interesting that we don't really see this in AIM v2. I think this is important to highlight. So AIM v2, even though it's also autoregressive, it's very, very different from AIM v1. So it's not really a next patch prediction task, but it's a multimodal. So they're training on text and vision, and it doesn't have the same trends as AMV1. But I think that's just because the pre-training task is very different. And it's called AIM. It is autoregressive in some ways, but it's just multimodal and very, very different from AMV1. So we don't see the same trends there. And we also see um, different trends for every single pretext task. So you could probably plot you could get a different prompt entropy line for every single pretext task that you want to look at. Um, but there's the thing to note here is there's two striations. So there's like the models at the top of the prompt entropy. So these are like the dynos and the clips and the supervised vision transformer. So they're kind of flat. And at the bottom of the prompt entropy graph, so that you have your BERT style model, which is the BEIT, and you also have your AMV2. Uh, which is it's just interesting to see how pretext tasks influence these representations. Um, so we'll kind of conclude now with just some implications of our findings. So most concretely, there's four key benefits of this paper. So the first is you can get better embeddings with like one line of code. It's very easy to get this performance boost by using your intermediate layers. Um, At the same time, you can improve your inference time. So using less layers, like if you want to use, let's say your 17th layer, for instance, in a 30 layer model, you can just chop off those last 13 layers and just use those first layers that you're interested in. This leads to less inference time. You can use a larger batch. It's just more efficient in general. Um, you can also These techniques also impart like a better understanding of the internal model behavior. I think any insight into the transformer black box is important these days. Just understanding how it's being trained, what's really going on inside. And there's already been some follow-up work too, um, where going beyond using our metrics as evaluation metrics only, you can also use them during training as a regularizer during training. So the Seek VCR paper optimizes prompt entropy. So it's essentially a follow-up work that optimizes prompt entropy, and it improved GSM 8K math reasoning for chain of thought reasoning on Quinn models. So not just evaluation, but you can also train with these metrics to get certain properties that you want in your model. Um, the last note I will leave on is, take action today and, check your intermediate layers. If you're doing some downstream task where you're taking a model off the shelf and applying it to your data set, just check your intermediate layers if you can. So for Hugging Face, that's like the little code snippet here. It's very easy. You can just say output hidden states equals true, and you get all of your intermediate hidden states. Yeah, and just check your intermediate layers, maybe from 20% to 70% of your model, and you can measure prompt entropy or any of our other metrics to find the best layers for autoregressive transformers in particular. Um, yeah, so it's just an easy thing to try, and I'm hopeful that it will improve your performance. With that, I'll thank everyone for listening, and there's my email if you want to reach out with any questions. And in the meantime, if you want to ask questions here, please do.